In this video, we are going to introduce our final thermodynamic concept, our final thermodynamic quantity, and that is Gibbs free energy, which is abbreviated with a capital G. If we're measuring the change in Gibbs free energy, we would measure it in delta G. So why do we need this new thermodynamic quantity? Why do we need a new thing, Gibbs free energy? Well, delta G is helpful because we've learned that delta S, when it's greater than 0, that usually means a reaction is spontaneous. But you can also have some reactions where delta S is less than 0 and a reaction is spontaneous. We've also learned that if you have delta H greater than 0 or delta H less than 0, these can also sometimes be spontaneous reactions, but not always. What we need is a function that will allow us to always predict whether or not a reaction will be spontaneous. Because remember, the purpose of thermodynamics is to predict whether or not reactions will happen and how far they will go. So what is the purpose of Gibbs free energy? Okay, it's to predict spontaneity. Okay, and with delta G, we can always predict whether or not a reaction will be spontaneous. The units for delta G can either be in kilojoules per mole or joules per mole. Either one. More commonly here, but sometimes with joules per mole. So how do we use this concept of Gibbs free energy to predict spontaneity? Well, there's one relationship, one equation that connects all three variables, delta G, delta H, and delta S, that we've learned about so far. And that relationship is here. Delta G is equal to delta H minus T times delta S. Okay. This is the equation that you need to know. It's on your equation sheet. A few things to point out. Since these all have knots at the top, they're all under standard conditions. 25 degrees Celsius, which is 298 Kelvin, and 1 atmosphere of pressure. This T here is the temperature, okay, in Kelvin. Okay. And delta H and delta G are just other thermodynamic values. So, how do we use this? Well, if delta G, if you do a calculation, you determine that delta G naught is less than 0, the reaction is spontaneous. Spontaneous. So delta G is negative, it's spontaneous. If delta G is positive, then the reaction is non-spontaneous. Or is it spontaneous in the other direction? And finally, if delta G is equal to 0, then the reaction is at equilibrium. So those are the three main things you need to know about delta G and how to predict whether or not a reaction is spontaneous. So let's go ahead and look at an example. Is the reaction below spontaneous at 298 Kelvin? Nitrogen gas plus oxygen gas produces 2 moles of nitrogen monoxide. We're given the delta H naught of the reaction is 180.7 kilojoules per mole, and the entropy of the reaction is 24.7. So, is it spontaneous? We need to know what is delta G. If delta G is negative, it's spontaneous. If it's positive, it's non-spontaneous. So, the equation we need to use, delta G naught equals delta H naught minus T delta S. Now let's just go ahead and plug in our values. So delta G naught is equal to delta H, 180.7 kilojoules per mole. 180.7 kilojoules per mole. Minus the temperature, 298 Kelvin. Times the entropy, delta S. Notice, warning, 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 warning. Entropies are always given in joules per Kelvin. So what you need to do is convert this into kilojoules before you plug it in, because the enthalpy is given in kilojoules. So I need to divide this number by 1,000. If I divide it by 1,000, I get 0.0247 kilojoules per mole. Huge warning there. Make sure you convert that into kilojoules before you do a calculation. Once you have it set up, then it's just the algebra from there. Multiply these two values together here, subtract it from 180.7, and if you do so, you get a final answer of 173.3. The units that I'm left with, kilojoules per mole. So, to answer this question, is the reaction below spontaneous? Since delta G is greater than 0, this is non-spontaneous. What does that mean? That means that it is spontaneous in the opposite direction. So if the arrow went like this, then that reaction would be spontaneous because delta G would now be negative 173.3 kilojoules per mole. Okay. That's what we need to do. I could also give you delta H's for the compounds, and you would need to get delta H of the reaction first and then plug it into this equation. Same thing with delta S. There's also going to be a lot of conceptual problems that are like that. So, let's predict spontaneity conceptually. Let's look at this equation. Delta G naught equals delta H naught plus, minus T delta S naught. So, let's say delta H is greater than 0 and delta S is less than 0. Can we predict spontaneity based on that alone? Well, let's go ahead and see. If delta H is greater than 0, then delta G is going to be equal to a positive number, whatever that is, minus some temperature times delta S is less than 0, a negative number. So essentially what I'm going to have is a positive number, negative and negative, multiply those together makes it positive, plus another number. So no matter what number delta H is, no matter what number delta S is, if delta H is positive and delta S is negative, since delta G has to be a positive number, the reaction will always be non-spontaneous in that direction. Always. Let's talk about another example. Let's say that delta H is greater than 0 and delta S is greater than 0. Then what's going to be the case? Well, delta G naught will be equal to, if delta H is greater than 0, a positive number, minus the temperature times the entropy, which is also a positive number. So this is going to be leaving me with a positive number, minus times positive is minus the temperature. Okay, so this doesn't always predict what the spontaneity will be. But let's think it through. In order for it to be spontaneous, this value needs to be less than 0. So how can I make this number negative? The only way delta G can be negative is if this value is bigger than this value. So if it's like 10 minus 20, that would give you negative 10, which would be spontaneous. So what would we say? If you have an enthalpy that's greater than 0 and an entropy is greater than 0, this reaction is spontaneous at high temperatures, high temps, because we need this value to be very big in order to make delta G negative. We could go through the other two combinations as well, but what you come out with as a summary, besides these two, is this. If delta H is positive and delta S is positive, the reaction is spontaneous at high temperatures. If delta H is negative and delta S is positive, the reaction is always spontaneous. If delta H is positive and delta S is negative, the reaction is never spontaneous. And if delta H and delta S are both negative, the reaction is spontaneous at low temperatures. So what you need to be able to do is predict spontaneity given qualities like this without numbers, using this reasoning here. Also, do the actual calculations to determine what delta G is to predict spontaneity. And understand, basically, as a warning, you've got to watch out for your units of delta S and delta H when you plug them into this equation.